All right, welcome everyone. So we're now recording. So any questions before we begin talking about the material for the class? Can everyone hear me all right and see what I'm writing here?
Yeah, we can hear you.
Great, thank you. All right, so last time we finished with the Leray spectral sequence. And I didn't have a chance to give you any examples of that, so I want to give at least one example and remind you what it is before we move on to the next topic. So let me remind you. So what this was we had a morphism x to y, f, and then y to z, g, and to this data we associated a spectral sequence, which had at the E2 page Ri g lower star of Rj, f lower star of a sheaf, and that converged on the E infinity page to Ri plus j of G composed with f lower star of your sheaf. Okay, and the content of this was we showed that pushforwards preserve injectives, and then we used that to deduce the existence of the spectral sequence from the general notion of the spectral sequence of a composition of functors. And then I tried to explain to some extent how to actually get your hands on the differentials, at least on the E2 page of the spectral sequence. Okay, so I want to give some examples, or at least one example, about how one can apply this. So suppose Z is spec K, where K is not necessarily algebraically closed. Well, let's do it this way, actually. So suppose I have X just to spec K, where this is some map pi, and K is not algebraically closed. So in this situation, I explained that a special case of the Leray spectral sequence was as follows. So one gets so really this is the spectral sequence for the composition of functors pi lower star followed by global sections. So one gets a spectral sequence going from the cohomology of K with coefficients in well, what I'll call Rj pi lower star of f, but I'll be explicit about what this is in a second. And this will go to hi of x Etale with coefficients in f. Okay, so this left group here is the Etale cohomology of spec K. So this is Galois cohomology, right? So this is Galois cohomology. So can anyone help me understand what Galois module are we actually taking the cohomology of here? So how do we go from a sheaf on spec K Etale to a Galois module, a discrete G module? Can anyone remind me how that works?
By taking the
K-bar points. Yeah,
so you're sort of taking the global sections on K bar. You're not literally doing that. You're taking the direct limit over all subfields of well, K sep. That's just because K sep is not an Etale cover of spec K because it's too big, but that's morally what you're doing. Okay, so if you unwind that, what you actually get is that the Galois module corresponding to Rj pi lower star f is what? Can anyone tell me? So what do you get when you take the K bar points of this functor? So it's the direct limit of all the cohomology of x k prime, where k prime is a subfield of k sep containing k, but that's just the same, and you should check this, as hj of x k sep with coefficients in f. Okay, so what does the Leray spectral sequence become? So it becomes a sequence HI of the field with coefficients in Hj of x k sep etale with coefficients in F. And this converges to Hi of x etale F. Okay, so just as an example,
why is it an I, not an I plus J?
Oh, you're absolutely right. It's an I plus J. Sorry about that. Yeah, so just as kind of a sub-example, let's consider the case where K is a finite field. And X over K is, let's say, a smooth affine curve, or maybe even a smooth projective. Well, let's say just a smooth projective variety. So in that case, Galois cohomology of a finite field is sort of easy to understand. So can anyone remind me what it is? So there's only two cases. It's I equals 0 and 1. We're just taking the cohomology of Z hat. So the exercise you should work out is that the cohomology of Z hat is as follows. So it's the invariance in degree 0, and it's the co-invariance in degree 1, and it's 0 in higher degrees. So what this tells us is that, for example, suppose we knew, and we'll prove later, that the cohomological dimension of a smooth projective variety over a finite field was 2n, or sorry, over the algebraic closure of a field was 2n. So this is, for example, if we put Z mod L to the n coefficients here, what that would tell us is that the cohomological dimension of X is going to be that plus 1. So it'll be 2n plus 1, right? Because just by staring at the spectral sequence. So in particular, and what am I saying? I'm saying this E2 vanishes as long as I is bigger than 1 here over a finite field. So this is some example of how you can actually use these spectral sequences to say something about Etale cohomology. So this is saying that it lets you understand Etale cohomology of varieties over not separably closed fields in terms of Galois cohomology and in terms of the cohomology of varieties over separably closed fields. Are there any questions about that example? Okay, and I do just want to mention for culture, and hopefully we'll get to this sort of thing later in the course. So there's a general fact about Leray spectral sequences for smooth proper morphisms, which is extremely useful. So suppose that x to y pi is a smooth proper morphism. And just for simplicity, let's just say of varieties over C. Although this will be true when stated appropriately in general. So then there's a Leray spectral sequence in sheaf cohomology for sheaves on the analytic site. The proof is exactly the same. So we get a sequence, a spectral sequence, which goes from the cohomology of Y with coefficients in Rj pi lower star, let's say of the constant sheaf Q, and this will converge to Hi plus J of X with coefficients in Q. So this is just singular cohomology of X. Okay, and then the amazing fact, which is due to Deligne, and the first proof was using Weil-Divisor, is that this spectral sequence degenerates to D2. Okay, and again, this is something which is proven via L-adic cohomology, so it's a sort of Etale cohomology with sort of QL coefficients in some appropriate sense we'll talk about later. And it fundamentally uses the theory of weights. So this one proof goes through Weil-Divisor. So this is a really, I think, amazing topological fact about morphisms of algebraic varieties. This sort of thing is very false for like smooth proper morphisms between manifolds. It's saying that cohomologically smooth proper morphisms of algebraic varieties behave a lot like products, rather than sort of much more interesting things which can be twisted up. Right. Are there any questions about that remark? I mean, this is just something I wanted to mention because it's very cool. All right, so with that, I want to finish up this section of studying pushforwards just by being kind of explicit about what pushforwards are and how to think about them, what these derived pushforwards are. So here's a proposition. Sorry, was there a question?
Yeah, I mean, maybe I want to ask: is this morphism to be proper very necessary in this remark?
Yeah, that's necessary.
All right. So if it's not proper, like, sorry, forget about it. Sorry.
That's all right. Cool. All right. Yeah. So let me now let's just try to be explicit about what these derived pushforwards we're studying actually are, and we define them kind of abstractly as the derived functors of the pushforward functor. So you compute those how? You compute those by taking an injective resolution and then pushing forward the resolution and then taking the cohomology sheaves of what you get. So I want to give another description. So suppose I have pi, which is a map from X to Y. Then the proposition is that Ri pi lower star of a sheaf F is the sheaf associated to the pre-sheaf, sending an open U on Y rather to the cohomology of the preimage of U. So let me write that as pi inverse of U with coefficients in F. Maybe let me be clear that I'm talking about Etale cohomology. Although this will be true in any site. Okay, so I mentioned this last time, but I didn't prove it. So let's prove it. So what I want to do is sort of break down the push forward functor. Well, before I prove this, are there any questions about the statement?
So here the morphism can be any morphism, right?
Yeah, this is any morphism between algebraic varieties, and I mean this will be true also for morphisms of sites.
Right. Thanks.
Yeah. Yeah. Thank you for the questions. Okay, so let's prove this. So first of all, how do we compute the push forward? So we choose an injective resolution. So this is an injective resolution of our sheaf F. And we take the cohomology sheaf HI of pi lower star of this injective resolution. And this is defined to be Ri pi lower star of F. Okay, so what I want to do is I want to compute this push forward functor in a different way, which will make things a little bit clearer. So here's one way of writing down the push forward functor. So we have sheaves on X Etale that maps to sheaves on Y Etale. That's what the push forward does. But let's think about what it does on pre-sheaves. So first of all, we can take the forgetful functor that pre-sheaves on X Etale. So this is forget. Then the definition of the push forward makes perfect sense on pre-sheaves. Okay, and the remark I want to make is that, okay, forget is not an exact functor, but pi lower star is an exact functor on pre-sheaves. Can anyone tell me why that is?
So you take any open set and just pull back.
Yeah, exactly right. So,
yeah.
So it's really just from the definition of pi lower star. So a sequence of pre-sheaves is exact if it's exact on every open. But okay, so how do we define pi lower star? Well, its values on opens of Y are values of your sheaves on of your pre-sheaves on other opens of X. So if you were exact upstairs, you're exact downstairs. Okay, and then we can sheafify. So I think I call that functor A, the sheafification functor, or the associated sheaf. Okay, can anyone explain to me why this diagram is commutative? Any thoughts? So I claim, first of all, that just as a bare functor, doing this is the same as doing this. And that you can just check on the values of your sheaf or pre-sheaf up here. So the question then is why when we apply A to this pre-sheaf we get here, why is it the push forward? So why does it stay the same? Any thoughts? Okay, well, the answer is that if you just compute directly, doing this is the same as doing this. So what you get over here is already a sheaf, and then sheafification sends sheaves to themselves. Are there any questions about that? All right, well, if not, let's use this factorization of pi lower star we've created to prove the proposition. So from above, to compute the derived push forward of F, we just take the cohomology of pi lower star of this injective resolution. Now let's factor pi lower star. So this is the cohomology of sheafification, so I call that A, composed with pi lower star, composed with forget, applied to I bullet. All right. Do you guys agree with this so far? All right, I will take that as agreement. All right, now I already explained that pi lower star was exact. Sheafification is also exact, so we can pull it out of this cohomology. So we're really taking A composed with pi lower star, the pre-sheaf version, composed with, or applied to rather, HI of forget I bullet. All right. So can anyone tell me explicitly how to think about this functor here? So HI of, if you just take the cohomology of the sequence of pre-sheaves I bullet?
It's exactly what it should be on the opens.
Yeah, exactly. So let's just think about this. So first of all, why isn't this 0? I bullet was an exact complex of sheaves. So the reason it's not 0 is that an exact complex of sheaves is no longer exact when you view it as a complex of pre-sheaves, right? Being an epimorphism in sheaves is different from being an epimorphism in pre-sheaves. So these groups are in general non-zero. And what are they? Well, if you compute them explicitly, they're the functors that send an open U to HI of U F. Okay, and what's the proof? I mean, just look at what like this I bullet restricted to U is an injective resolution of F, so that you're exactly computing this cohomology. Okay, so what are we saying now? Now we're done, right? So now let's evaluate this on an open of Y. So now this functor over here, the push forward, sends an open of Y, so U to Y, an Etale open, it sends to, well, it's pushing forward. So this is taking the cohomology of pi inverse of U with coefficients in F. Okay, and now we're sheafifying that. So that's exactly what we wanted to prove. Are there any questions about that? All right, so let's do an example. So let's suppose that X is let's say an integral scheme. And eta, including into X, is the generic point. So what I want to understand is, and so let's suppose we have some sheaf F, which lives in sheaves in eta Etale. So maybe let me call this inclusion iota. So the goal is to understand iota lower star of F, or Ri iota lower star of F. Okay, so when I say understand, can anyone help me make sense of that? So like what is the best way to understand a sheaf in your view? Let me turn on the lights here.
I mean, like, give its values on the, like, objects.
Yeah, so we probably can't quite give values. We can say it's the sheaf. We could unwind this theorem we just proved and say it's the sheaf associated to some fairly explicit pre-sheaf. But what we can do is maybe compute its stalks, right? So let's try to compute its stalks. So let's suppose that x bar to x is a geometric point. So let's compute Ri iota lower star of F and the stalk at x bar. Can anyone help me do this? So can anyone remind me what the definition is?
So we're going to take a direct limit.
Yeah. So what is this? So this Ri iota lower star of F x bar is the direct limit over u bar. So this was an Etale neighborhood of x bar. So let me remind you what that meant. So u is an Etale mapping to x. U bar is a geometric point of u mapping to x bar. And what are we taking the direct limit of? We're taking Ri iota lower star of F evaluated at that u. Can anyone help me unwind what this is? Any thoughts? How do you compute a derived push forward, or how do you compute the stalk of a, let's say here what we're trying to do is we're trying to compute the stalk of a sheaf which is associated to some pre-sheaf we know. So how do you do that?
So I guess sheafification preserves the stock, so you can just, yeah.
That's exactly right. So it's the same as the stalk of the pre-sheaf, which is what? So what we can do is write the same limit on pre-sheaves, right? So this is the same as hi u eta with coefficients in F restricted to u eta, right? Okay, and then the claim, and this is really just an exercise in unwinding definitions. So this is an exercise, and you should do this exercise, is that, so let me define Ox x bar to be the stalk of Ox at x bar, and then Kx bar to be the fraction field of Ox x bar. Then the claim is that this stalk, Ri iota lower star of F at x bar, is just the same as Hi of Kx bar with coefficients in F, well, restricted to Kx bar. So when I say restricted, I just mean the pullback. Are there any questions about this? So these rings have a name. So this is called the strictly Henselian local ring. of x at x bar, and this is called the strictly Henselian field. Associated to x at x bar. Okay, so what is this saying? What you're supposed to think is that these are the Etale analogs of local rings, and this is saying you can compute the stalk of a cohomology sheaf in terms of the cohomology of these strictly Henselian local rings. So this is an important exercise, and if you're registered for the course, I insist you do it, and it would be nice, for example, if you came to office hours and explained to me your solution, or if you failed, ask for help. But I want you to give it a try. Okay, and it really is, I claim, an exercise in unwinding definitions. All right, are there any questions about this? So this is saying we understand the cohomology of a push forward from a generic point.
Sorry, is it the group cohomology you're writing on the right-hand side?
I'm sorry? Oh, so this is, you can think of it either as Galois cohomology, because it's cohomology of a field.
Yeah.
Or you can think of it as the Etale cohomology of spec kx bar Etale. And
okay.
we showed that those two things are the same. All right, so now, so that's the sort of, and most of this stuff is more or less formal, although very important. So I want to now return to remind you what our goal was. So let me remind you. So our goal was to understand hi of x GM, where here x is a curve over a separably closed field. And so far we've succeeded in understanding 1 and 2, hi for I equals 0 and 1. So we need to understand this for I bigger than 1. And the goal will be to reduce it to some computations in Galois cohomology. So this proposition or this claim I just made for you will be sort of the key input. Well, the key formal input, and then we're going to have to actually do some computations in Galois cohomology. So now what we want to do is we want to reduce this question to questions in Galois cohomology. Which we'll then try to answer. So how will we do that? Well, how are we going to relate the cohomology of GM to the cohomology of GM on some fields? So here's the relevant proposition. So let's let x be a regular integral variety. I guess varieties are integral, so a regular variety over a field K. And the proposition will hold in slightly more generality than that, but let me state what we're going to use. And let's suppose that eta, including into x, is the generic point. Then there is.
Is K algebraically closed here?
No. Or not necessarily, it could be. Then there's a short exact sequence of sheaves. Maybe I'll write that as short exact sequence in sheaves on x Etale. I mean, this theorem will be true in a lot more generality than I'm stating it. Even it will be true for x equals spec z, for example. But let's just state it in this generality for now. So there's a short exact sequence going from GM to eta lower star of GM. So if you'd like, if you'd like, you can think of this as either eta lower star pushing forward GM from the Etale side of eta, or you can think of you're taking the pullback of GM to the Etale side of eta. That's just GM and then pushing it forward again. And then, does anyone have a guess as to what the co-kernel of this map is? Peter, you unmuted.
Divide the group.
I'm sorry?
Divide the groups.
Yeah, it's the sheaf of divisors. So one way of writing this is it's the direct sum. Sorry, the direct sum over z in X of codimension 1 of iota z lower star of the constant sheaf z. Okay, and the constant sheaf z is something a little weird that we haven't really thought about in this class yet, but we'll think about it now. Okay, so can anyone help me prove this? So first of all, what is this map? This first map? Can anyone tell me what that is?
Which map? Sorry.
This first map here from GM to eta lower star of GM.
Do we just restrict the section to the generic point?
Yeah, exactly. This is just restriction. If you'd like, you can think of it as, I would have to think of which one it is, either the unit or the co-unit of the adjunction between eta lower star and eta upper star. But that the less fancy way of saying that is it's precisely restriction. Okay, and then this map is the one that sends, well, what is a section to eta lower star GM? Well, on a Etale open of X, so an Etale morphism U to X, this is just a bunch of rational functions, a rational function on each component, and you can take the divisor of that rational function. And that will give you a number for each codimension 1 point, namely the order of vanishing of your rational function on that codimension 1 point. And all but finitely many of those numbers will be 0, so you'll get a section to this sheaf. Okay, so can anyone prove to me that this sequence is exact? So we've made a sequence, so we want to prove its exactness. So any thoughts? So there's 3 things we have to do. So first of all, we have to show that GM to eta lower star of GM is injective. So why is that?
Separatedness or something?
Can you say more?
Because if two sections agree on the generic point, then they should agree on an open subset.
I see. You're saying separatedness of the pre-sheaf GM. Sure, yeah, that's right. So this is you made it concrete though. You said that if a rational function vanishes at the generic point, then it vanishes. Or if it's really what we have to show is if it's identically 1 at the generic point, then it's identically 1. So what are we saying? We're saying that GM of U to GM of the fiber of U over eta is injective. That's what we want to prove. Because what is this? Well, this is OU cross, and this is the direct sum, if you'd like, of the fraction fields of, maybe I'll write it as O eta I, where here eta I is a generic point of U. Okay, and this is injective. Okay, and this already is using something, right? It's using, for example, that X is reduced. No, sorry. This is okay in general, actually. Okay, so 2, what do we have to show? We have to show exactness in the middle, right? So we have to show that if we have an F in eta star GM of U, such that the divisors of F are 0, this implies that F comes from GM of U. Can anyone tell me why this is true? So what is this saying on affines?
That it's invertible, right? That it doesn't have any zeros or.
Yeah. So if you're trying to show your function is your rational function here is what this is. This f is literally a rational function on u, or on each component of u. And what you want to show is that if it has no divisors, then it's actually a regular invertible function. So it and its inverse are both regular. So it's enough to show f is regular because then by the same argument, f inverse will also be regular, which is what we also want to show. So why is that? So what is the fact we're using? What we're using is that if we have a ring A, it's the intersection. So here, this is a finite type ring over a field of its localization at all its height 1 primes. So this is precisely, so being in this intersection is precisely saying that all of your divisors are non-negative. And so this is exactly what it means for A to be regular. So this is the commutative algebra fact we're using. Okay, and if this isn't familiar to you, that's something to maybe make me look up in T.M. McDonald. Are there other questions about this? Okay, and now 3 is going to actually use regularity. So far we actually haven't used regularity. So 3, we want to show that eta star GM with the direct sum over Z of codimension 1 of iota Z lower star of the constant sheaf Z is surjective as a map of sheaves. So what do we need to show?
So every divisor is locally principal.
Yeah, that's exactly right. So that's what we're trying to show, and we're trying to show that well, Etale locally, but in fact it's true, as maybe you suggested implicitly, it's true Zariski locally. So can anyone explain why that is?
I guess because everything is Cartier because it's regular.
Yeah, that's exactly right. So what we're trying to show here is that every Weil-Divisor, so a global section to this sheaf on the right is a Weil-Divisor. We're trying to show it's locally principal, which is just the same as being Cartier. And that's true by regularity. Okay. So that completes the proof. All right, so what have we gained from this? So we now have this short exact sequence. So what does that give us? Anyone? What do you do with that short exact sequence of sheaves?
Take cohomology.
Yeah, so let's take the cohomology. Okay, so the corollary is that there's a long exact sequence going to h from h minus 1. So, well, it starts somewhere here of x Etale with coefficients in this divisor sheaf to hi of x Etale with coefficients in GM. So this is the thing we've been trying to compute. This goes to hi of x Etale with coefficients in eta lower star of GM. And then finally to hi of x Etale with coefficients in this divisor sheaf again. And then it keeps going. Okay, so now what's the point? The point is that these things, so these sheaves here, we can compute with the Leray spectral sequence. Right, because we're taking the cohomology of a push forward. Or at least these are sheaves that in principle appear in a Leray spectral sequence. All right. Are there any questions?
Don't you also need that AP is a DVR? Because you need that if if you have a fraction and the both
Sorry, you're
divisor
right.
at the top equals
So you're saying for part 2, yeah, I think I need normality here. Yeah, so you're right, I used regularity in part 2. So this is, again, this is by, for example, normality. Yeah, you're 100% right, sorry about that. And so regularity implies normality. And in particular, regularity in codimension 1. Yeah, that's a very good point. Sorry, was that what you were pointing out?
Yeah, because I was saying it's possible otherwise to have divisor 0, but not in AP.
Yeah, no, you're 100% right. Yeah, sorry about that. Cool. All right, so let's compute these things.
Sorry, just a quick question. If we have something that's normal and not regular, then does this still hold? Or
the sequence will be left exact, but not in general right exact.
and the issue is that
So you might have Weil-Divisors which aren't Cartier.
okay, cool. Thanks.
Yeah. So you don't, I think you don't quite need regularity, but you need some, maybe locally factorial or something.
Is the co-kernel of the left map always the sheaf of Cartier divisors?
Is the co-kernel of the left map?
Right, because you put like the Weil divisors on the right hand side, but if you had like a more general situation, like normal.
Let me think about that. That sounds right to me. I have to think a little bit about what exactly that means. Maybe I would say maybe that's the definition of the sheaf of Weil divisors. Or sorry, of Cartier divisors.
Okay, thanks. I was thinking an analogy with like the exact sequence K cross to K cross mod O cross.
Yeah,
Okay,
yeah.
O
I'm just
cross.
worried that that if you make a naive definition, it might actually not be a sheaf, right? So what's clear is you'll get a pre-sheaf, and I think it's not too hard to see that its sheafification will be the co-kernel of this. But I would have to think a little bit just to think if what you're defining just on affines would actually give you a sheaf in the Etale topology. Yeah, but I just don't know off the top of my head. It's a good question. Yeah. Does that answer your question, at least sort of?
Yeah, thanks.
Cool. Okay, cool. So let's use this corollary. Okay, so let's actually start computing these groups. So first of all, suppose X is a curve over a separately closed field. By curve, I guess what I'm going to say is actually true with no assumptions. So I'll just say a curve. Then the cohomology on X Etale of this direct sum over Z of codimension 1. So that's just closed points of X of iota Z lower star of Z is 0 for I bigger than 0. Okay, can anyone help me prove this? So how would you get at something like this?
I guess the cohomology commute with the direct sum and
Great, so it's enough to show. That for Z and X, codimension 1, hi of X Etale of iota Z lower star Blackboard's bold Z is 0 for I bigger than 0. Great, so how would you show that? Any thoughts?
Well, like use the Leray.
Yeah, so let's use the Leray spectral sequence. So there's a Leray spectral sequence which goes from hi of X Etale rj, that should be upper j, our upper j of iota z lower star of z, and this converges to hi plus j of z Etale with coefficients in the sheaf z. Okay, so can you help me? Let's try to unwind these things. So first of all, what is rj lower of iota z lower star of z? Can anyone help me compute this? So in degree 0, so j equals 0, this is iota z lower star of the sheaf, the constant sheaf z. What about in degree bigger than 0?
For a closed immersion, it should be 0, right?
Yeah, that's exactly right. So we proved that push forward for closed immersions is exact just by checking on stalks last time. I think it was last time, which means that the higher derived functors are 0. Great. So what about, let's now compute hs of z Etale with z coefficients. So here z, just remember, is a closed point of a curve over an algebraically closed field. So for s equals 0, this is just z, right? It's global sections. What about for s bigger than 0?
It's an algebraically closed field, right? So it shouldn't have any cohomology.
That's exactly right. Yeah, so we're working with a separably closed field, or algebraically closed field if you want. So this spec of such a thing has trivial Etale site. It's the Galois cohomology of an algebraically closed field is 0 in degree bigger than 0. Okay, so that computes the proof. So what are we getting? We're just getting so that means that we're getting a special sequence which just has one column, so it's degenerate, right? So this implies the spectral sequence is degenerate. So we just get that hi of x Etale of iota z lower star of z, so this is the only term that survives, is equal to hi of z Etale with coefficients in z. And we just computed that, so that's z for I equals 0 and 0 for I bigger than 0. All right, it's 10:25, so maybe let's take a 2-minute break. I'm sorry, I've been missing a lot of chats. Oh, sorry about that, Ben. I didn't see you were typing things in chat. So let's take a 2-minute break, and I'll be sure to pay more attention to the chat when we get back. And then we'll continue and get to some real computations. All right, see you in a little bit. All right, everyone, I'm back. How's everyone doing? Anyone have any questions? So what did we do? So what have we done so far? So we've constructed exact sequence of sheaves, and hence a long exact sequence here in this corollary, and we've just computed the cohomology of this hi. So what does that give us? That this sheaf of divisors has no cohomology in degree bigger than 0. So what does that tell us? So that tells us that if X now is a smooth curve, so we need that to get that short exact sequence. So a smooth curve over K, a separately closed field, then what? Then we get HI of X Etale with GM coefficients is canonically isomorphic to HI of X Etale with coefficients in eta lower star of GM for I bigger than 1. Does everyone agree with this corollary, or does anyone have any questions about it? So we need I bigger than 1 so that the groups on either side in this long Zeph sequence we wrote down just now actually vanish. Okay, so are there any questions about that? All right, so let's try to compute this. So let's try to compute this group. So now we're going to compute we'll start computing this group. So that's the new goal. So what we've been interested in is this left-hand group, and now we've reduced it to something which is maybe not quite Galois homology, but it's at least pushed forward from a field. Okay, so can anyone tell me how they might start trying to get their hands on this group on the right-hand side?
Like exactly the stuff we were doing before.
Yeah, so we're going to try to use the Leray spectral sequence again. So what do we get? So what we get, so now we get the Leray spectral sequence. That gives us a E2 page of HI X Etale with coefficients in RJ eta lower star of GM. And this will converge to Galois homology. So this will converge to HI plus J of eta with coefficients in GM. Great. So for those of you who know a little bit of Galois homology, this object on the right-hand side might feel a little bit more approachable. So that's the Galois homology of a field with coefficients in the invertible elements of its algebraic closure. Okay, so let's but we're not interested in this whole left-hand side. We're just interested in the sort of leftmost row of Leray spectral sequence, so the part where J is 0. So let's try to understand these sheaves. So let's try to understand RJ of eta lower star of GM. And when I say understand, I mean let's try to understand what the stalk is at a geometric point. So can anyone tell me how to understand that? So we just talked about this at the end of our discussion of pushforwards before we got into this Weil-Divisor exact sequence stuff. Any thoughts? So can anyone remind me what the stalk of a derived pushforward is?
Going to be the Galois homology of the.
Yeah. So this is HJ of the Galois homology of what field? So it's the strict henselization, the strictly Henselian field of X at X bar with coefficients in GM. Right? Does everyone agree with this? So this was this exercise claim that I gave right before we started talking about the Weil-Divisor exact sequence. Okay, so now our goal is twofold. So we want to understand these groups. So I claim that we win if we can prove the following theorem. So suppose K is either the function field of a curve over an algebraically closed field, or separably closed field, or K equals the one of these kx bars. So the strict henselization, strictly Henselian field, associated to a geometric point. Of a curve over an algebraically closed field, or separately closed field. Well, let me keep writing algebraically closed field. So then the theorem is that hi of k with coefficients in GM equals 0 for I bigger than 0. So this is what we want now. So can anyone tell me why this suffices?
It shows that the push forward is 0 because all its stalks are 0, and it shows the
Yeah. So this, why does this suffice? So this suffices because, well, first of all, one, it shows that Rj eta lower star of GM is 0 for j bigger than 0. So then we get a special sequence hi x Etale eta star GM. Well, there's no j's, so this is just going to be equal to the infinity page hi of eta GM. Okay, but now again we apply the theorem. So to get one, we applied the strictly Henselian part of the theorem. Now to get this to be 0, so this is 0 if I is bigger than 0. Well, now we apply the theorem with the first part of the theorem, the case where k is the function field of a curve. All right. Are there any questions about that? So we've now, so the upshot is that we've reduced this computation of the Etale cohomology of a curve to Galois cohomology. All right. So does anyone have any questions about that reduction? All right. So now, I mean, so far most of this has been fairly formal. So I would say the sort of commutative algebra input here has been this Weil-Divisor exact sequence, and the rest of it was manipulations with derived functors essentially. So this goal theorem is definitely not formal. So we're gonna spend a fair amount of time talking about it, and it's gonna lead us to one of my favorite topics in this course, which is Brauer groups. So Brauer groups. Before I start talking about Brauer groups, maybe I should pause for 10 more seconds to see if there are any other questions. So if you are lost, this is your time to jump back on because Brauer groups are amazing, and it's going to be a lot of fun kind of geometry and in my view very cool ideas. So this is fun and very classical stuff. So I'm going to describe Grothendieck's approach to the Brauer group. So I'll be working over a pretty general base, but the classical theory is over fields, and that's all we're going to use. So at some point I'm going to specialize to the case of fields, and then we'll prove this goal theorem. But I want to introduce the key sort of geometric idea, which is the Brauer group. So let's get started. So here X is just going to be a scheme. And here's the sort of more formal version of the definition, which I'll very quickly start ignoring, but I want to give it to you because it's the most closely related to the course. So this is the definition of the cohomological Brauer group. So what is it? So I'm going to call it Br superscript co of X. The cohomological Brauer group of X is you take the Etale cohomology of X, the second Etale cohomology of X with GM coefficients, and then you take the torsion in that group. So this is what we're going to study. And as written, it doesn't feel like we've made any progress. We've just defined a group we already knew how to define with a different name. But the point is that in good situations, this group has a very geometric interpretation. So let me now define the actual Brauer group. So what we're going to do is we're going to try to understand this geometrically. In terms of PGL torsors, PGLN torsors. Okay, so my first claim, and this is still what I'm trying to build up to here is the definition of the actual Brauer group as opposed to the cohomological Brauer group. So my claim is that there's a natural map from the union of over all n of the set of Etale locally split PGLN torsors to H2 X Etale GM. So I claim there's just a natural set theoretic map like this. Can anyone tell me how to define it?
I guess there's an exact sequence, GM to GON to PGON.
Yeah, so that's the sort of idea, and then we're going to have to think a little bit to make that rigorous. So the idea is that there's a short exact sequence of sheaves of groups, GM to GLN to PGLN to 1. So this is a short exact sequence in sheaves of groups on X Etale. It's not obviously exact. It's not obviously right exact. Can anyone tell me why it is? So in particular, what I mean by that is it's not obvious a priori that this map from GLN to PGLN is a surjection of sheaves. So this is, let me just say the reason. So this is right exact. The key input is that GLN to PGLN is smooth. And hence has sections Etale locally. So it's a general fact that smooth morphisms have sections Etale locally. You could also prove this functorially. So what is a map to PGLN?
It's just a matrix of functions, well, equivalence relation of matrix of
so can you say
functions.
explicitly what you mean by that?
So like in terms of so a map into GM would be like the unit like invertible regular function. Then in that sense, like I have like invertible matrices of regular functions.
Yeah, so that's a map into GLN.
To scaling
So what about a map into PGLN?
Like exactly the definitions that
Sorry, you're breaking up a little bit. Yeah, so I think what you were going to say is you take an invertible matrix of functions and then you plot out by. Sorry, go on.
I'm sorry, it lagged a bit. I didn't hear.
Yeah, so I think what you were going to say is that you take an invertible matrix of functions and then mod out by scalars. Is that right?
I can't hear. I'm sorry, it's a bit laggy. I couldn't exactly.
Oh, sorry. Yeah. Are other people having trouble hearing me? Yeah. So what I was saying is I was just trying to guess what you were trying to say, Ollie, which is that your claim was that a map into PGLN is an invertible matrix of functions mod scaling. Is that what you were saying?
Yeah, exactly.
Yeah. So that's not quite right, actually. So locally, that's what it is. But that if you think about it, it won't be a sheaf. So what it is it's the sheafification of that. Yeah. So that's why it's not totally obvious. But in fact, I mean, here we can really make a much softer argument. So here, this map GLN to PGLN, it's actually it's a GM torsor, right? So what do we know about GM torsors? Okay, so GM torsors are Zariski locally trivial. So in fact, this sequence is actually exact in the Zariski topology. Okay, so in particular in the Etale topology. Okay, so let's really be concrete about that. So can anyone help me go? So let's actually try to really write this down. So suppose T is an Etale locally trivial PGLN torsor. So what we want to do is try to use the long exact sequence associated to the short exact sequence of sheaves. So we want to use long exact sequence, and which has in it morally H1 of X Etale PGLN. So that's PGLN torsors to H2 of X Etale GM. So we're trying to use this map. Okay, so this doesn't really make sense, at least a priori, because this is not a sequence of abelian sheaves. So Ben asks if PGLN is an affine scheme. It is actually an affine scheme, but it's not totally obvious. So that's a good exercise. So so could I give an example of a U and a section of PGLN that's not in the image but is in the image after a base change? Let me think about that for a second. Yeah. So you should be able to give an example on any scheme with a non-trivial Picard group. So I think, yeah. So the sort of thing you do is if you take a map from V to V tensor L, where V is a vector bundle and L is a line bundle, Arvind, this in general will give you a map. So this will give a map to PGLN, which won't in general come from GLN. So what you should think about this is think about the and yeah. So maybe let me give the simplest example. So suppose I take a map from O direct sum n to L direct sum n, right? So this gives you an endomorphism. So this gives you a endomorphism of a trivial projective bundle. So which is the same as an element of PGLN, but in general, there's no reason that endomorphism should come from an endomorphism of O to the n. Does that answer your question, Arvind?
Yeah, maybe I'm being too naive because I'm trying to think about this stuff in terms of like literally there's a family of matrices over the U, and then
yeah. So what you're supposed to think is say you take I mean the abstraction to doing this is exactly a line bundle. So what you're supposed to think is take an open cover, take maps to PGLN on that open cover, which you can think of as literally being representable by matrices, right? Here's one way they could glue to a map to PGLN. Well, they agree after you quotient by scaling, but there's no reason why you should actually be able to lift those, why you should actually be able to change those maps to something that agrees without quotienting by scaling.
Okay, cool. I think I'm happy with that for now.
Yeah. So this is the sort of general situation. I mean, in fact, what's true is that there's a map from H0 GLN, so that's maps to GLN, to H0 PGLN, and this maps to H1 of GM. So really the obstruction to surjectivity here is literally a line bundle.
Cool, thanks.
Yeah.
So
So that's
that-
kind of the low degree version of what we're about to try to write down in terms of torsors.
And that line bundle is given exactly by like the overlap, if you have a matrices that are the same after you quotient, then there are going to be some ratios of functions on your cover, and those give you a cocycle for the line.
That's exactly right. That's 100% right. Yeah. So that's exactly that map from H0 of PGLN to H1 of GM that I just alluded to. Yeah, that's perfect. Okay, so let's try to do that one cohomological degree up. That's exactly what we're trying to do. So let's suppose I have an Etale locally trivial PGLN torsor T, and I want to give a map. So I want to associate to this some class T in brackets in H2 X Etale GM. So how do I do this? Can anyone help me out? So how do we describe such a T? Let's try to write down first. Let's try to write down T in H1 check of X Etale PGLN. So can anyone remind me how one does this? How does one get a kind of PGLN cocycle out of a torsor?
We use isomorphism from T cross T to once it trivializes over itself.
Yeah, so here we said it's Etale locally trivial, so we'll choose a trivializing map U to X, so that T restricted to U is the same as PGLN restricted to U. So from this, we get a cocycle. So we get a cocycle in, well, what is it? It's a map from U cross U over X to PGLN, right? So what next? All right, so what next is that we'll come back to this next time, and you guys can think about it, because we're out of time. All right, so I'm gonna stop recording, and then next time we're gonna dive deep into the Brauer group. It's gonna be awesome. All right, see you guys next week, I guess, but I'll stick around for a bit if anyone has any questions. So I'm gonna stop recording now.